We're going to talk about group homomorphisms today, and this should bring you back to our discussions about ring homomorphisms and homomorphisms of fields. Remember that we talked about these functions being algebra preserving. Well, in the case of a group, we want to preserve the group operation. That means that if we have a homomorphism of groups going from G to H, when we plug in a product in G, like A star B, we should get a product in H that looks like f of A star f of B. And normally, again, we write these things just with juxtaposition, but for the purposes of this first example, I used a star to clarify where these operations come from. Now remember that an isomorphism is just a homomorphism, so a function that preserves algebra, that is also one-to-one, or injective, and onto, or surjective. So, an algebra preserving bijection is what we mean by an isomorphism of groups. When we have an isomorphism between two groups, like let's say our homomorphism f from G to H is an isomorphism, we say that the groups G and H are isomorphic. And we write G isomorphic to H with that little symbol in between them. And if you see that symbol all alone, if you see G isomorphic to H, what that means is that there exists a function f from G to H that is an isomorphism of groups. So if you're asked to prove that something is isomorphic to something else as a group, what that's really asking you to do is to cook up a function that acts as a group isomorphism. Take a look at these examples at some point on your own, and if you have any questions, make sure to post them on Piazza so that we can talk a little bit more about them. Where have we heard the word group before? Well, we've heard it in Galois groups. We're going to use group homomorphisms, and in fact, group isomorphisms, to take Galois groups, whose elements are those kind of complicated automorphisms of fields that fix a base field, blah, 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 and instead think of them as subgroups of symmetric groups, our permutation groups. So we can write down Galois group elements as permutations of the roots. And this makes it simpler to deal with, and because our function is algebra preserving, that's what we like about homomorphisms, it says that we're not really changing the structure as long as we're working with an isomorphism. All right, to reiterate, one more time, our goal is to make our lives simpler by thinking of the Galois group as isomorphic to a subgroup of a symmetric group, where n is the number of roots of our polynomial p of x. Now, we haven't talked about subgroups yet, but we will, so don't worry. And the tool that we're going to use to transform our Galois groups into subgroups of these symmetric groups is the idea of permuting the roots to define a larger function that acts as a group homomorphism. Our function t is going to go between the Galois group, so it starts with the domain being the Galois group of f of p of x over f, and its codomain is going to be the symmetric group on n elements, so the set of permutations of n things. And we may not have an onto homomorphism here, but we're going to have a one-to-one homomorphism. And so we're going to show that. That's our next proposition. The way that we define our function t is we take an automorphism that from f of p of x that fixes f, and we send it to the way that it permutes the roots of p of x. That's what that f restricted to r notation means. So t of an automorphism becomes a permutation of the roots of the polynomial p of x. Is this a function? Well, yeah, f is a permutation of the roots in exactly one way based on the polynomial p of x. That's what it means for that automorphism to be completely determined by the way f permutes the roots of p of x. Does this function preserve algebra? Well, let's check. Okay, so we plug in a composition, f composed with g, and we want to see what happens when we evaluate this thing at the roots. Do we get a permutation, and does our algebra end up being preserved? So is this going to be the product of the permutations f restricted to r and g restricted to r? But it turns out that this is just a matter of definition. And so we get exactly what we want. We get that this is really just a product of permutations in Sn. The last thing to verify is that this is really one-to-one. But if t of f and t of g are the same thing, that means that f and g preserve the roots in exactly the same way, and so they determine the same automorphism in the Galois group from an earlier proposition back in chapter 12. So we do have a one-to-one group homomorphism from T from the Galois group to the symmetric. What this really means for us, this one-to-one group homomorphism T from the Galois group to the permutation group, is that we can rewrite our automorphisms as cycles, because we know that we can write permutations in cycle notation. So the first thing to do in order to do this is label the roots by numbering them. Okay, and then once we have A1 through AN, we can look at our table and figure out exactly where these roots go by applying our automorphism F to them, which really means just plugging these roots into whatever automorphism F we're dealing with. And let's pick an example. Let's do F3 in the table. So the first thing I'll do is I'll just remind you of our convention here. As in the notes, we're going to label our roots as A1 is cube root of 11, A2 is cube root of 11 zeta 3, and A3 is cube root of 11 zeta 3 squared. Why are these the roots of the polynomial x cubed minus 11? Well, that's something that we talked about way back in chapter 3. But once we find one cube root of 11, we find the others by multiplying by the remaining roots of unity. When we plug A1 into F3, we end up back at A3. So this is going to be a permutation that sends 1 to 3. And let's figure out what it does to A2 and A3. So first, when we plug in cube root of 11 times zeta 3, we realize that we're going to use both rows of our table here, and we're going to break this up using the fact that our automorphism preserves multiplication. And so cube root of 11 ends up going to cube root of 11 zeta 3 squared, and zeta 3 is fixed. Zeta 3 goes back to zeta 3. And so when we multiply zeta 3 squared times zeta 3, we get zeta 3 cubed, or 1, and thus we end up with cube root of 11, which is A1. And now because this is an automorphism that permutes the roots, and I've already sent A1 to A3 and A2 to A1, that means that A3 is going to have to go to A2, but let's just verify that. And if you take a moment to check my arithmetic, you'll see that this actually works out, because at the end of the day, we end up with cube root of 11 zeta 3 to the 4th, but again, zeta 3 cubed is just 1, so we end up with cube root of 11 zeta 3, which is A2. That means that we can rewrite our permutation F3 using cycle notation by saying that it takes 1 to 3, 3 to 2, and 2 to 1. So T of F3 is the 3 cycle, or the tricycle, 1, 3, 2. We're going to get a lot more practice doing this because it's one of the key things that connect up the structure of groups with the roots of polynomials later on in the course. But one thing that you'll want to notice in the example on the previous slide is that the homomorphism we just looked at, we know it's one-to-one because we proved that it has to be, but it's also onto, and that means that it's an isomorphism. The way that we use this is to identify the Galois group of Q adjoin the roots of x cubed minus 11 over Q by saying instead of Galois blah 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 blah, we just say that the Galois group is S3, because as algebraists, we really only care about the algebraic structure. And that's really nice because as a group, S3 is much nicer to deal with than a group whose elements are automorphisms of some field that fix some base field. And that is the end of this short chapter on group isomorphisms and homomorphisms. We're going to see that we can get some structure from groups by looking at special kinds of sets within groups, and that's where we'll head next. But until then, be well, stay healthy, and I'll see you next time.